So hello, welcome to the Arduino workshop series brought to you by UCR UAS. I'm Jonathan Tsai. Before we begin the main part of the workshop, we're going to start off with an announcement by Trang.
Alrighty, so I'm not sure how familiar you guys are with our workshop, but as always, our sessions will be recorded and materials such as the slides, the syllabus, and other guides will be posted onto our website at ucr.us.weekly.com. We will also have optional office hours after class from 6 to 7 p.m. In addition, we have some upcoming events. We have a social night next week on Friday. We're going to play Broken Picture Phone. And we have a banquet coming up on week 8. So we're going to just talk about a year in review of UAS and the stuff that we've been doing, what to expect for next year. So make sure you come over on Saturday. So yeah, that's it from me.
Okay, thank you, Trang. So next, we're going to have a presentation brought to you by Jeremy Carlton. Take it away, Jeremy.
All right, thanks, Jonathan. So what you're seeing in the video on this slide is a recording of a light show being played on a physical circuit in real time. So like the way we've been running this workshop since it's being done remotely is that any work you do on an Arduino, any testing of your code is done using a browser program called Tinkercad. But we wanted to give you a chance. Basically, we had this light show project where you would be controlling this set of 9 LEDs using an Arduino and basically light them up in whatever sequence you want to make a light show. And we're offering to let anyone who submits their code to us basically use one of our Arduino boards to get a recording of their code running on the physical circuit, the same one that you're seeing in action right now. And so this was all gone over in the previous session of this workshop, which is session 2, and you can access the recording of that through our website that I believe Trang mentioned in the announcements. And basically we're still accepting submissions. The code you're watching play out right now is actually a sample code because we haven't received any submissions from participants yet, but we'd love to have a chance to put something more interesting in action. So if you want a chance to learn more about the fundamentals of controlling circuits with an Arduino, then you can go do this project after watching the recording for session 2 if you haven't already, and then in that recording it'll tell you how to submit your code, and then if you do that, then during next session, which will be session 4, we'll be able to play it for you in the slides. So with that out of the way, I'll pass it back to Jonathan.
Okay, thank you, Jeremy. So now it's time for the main topic. We are going to go over how to run photoresistors and servos with your Arduino. So first we're going to take a look at what these components are, as well as a few of the basic decision making when it comes to building around these parts. Then I'll show you an example problem and show you how to navigate each of the setups for how you want to build the code. And then finally, we'll give you an assignment, and that assignment will help you practice and nail down each of the skills that you were showcased here today. So we'll start off with photoresistors. So essentially what a photoresistor is it's a resistor that changes based off of the light intensity. Okay, so it kind of works like a solar panel, where the brighter the light that it's exposed to, that'll actually lower the resistance level and allow the current to flow through better. Okay, so at the bottom, you can see the generic symbol for where you'll see them in schematics. So here you see a resistor with a circle and light going into it. And then on the bottom right, okay, you'll see how they're built. So what you want to do is you want to have your metal contacts, aka your terminals, located at the N pluses. You have your active layer, or the CDS, the conductive material, right in the middle. And then finally, you have your insulating layer at the very bottom to make sure that you can keep as much of the current inside of your circuit as possible. Okay. So the last image is essentially how they're built. So here you can see that it has the CDS track right in the middle, and that separates the two conductive locations on the left and right. Okay. So if you were to get your own photoresistor, here are some things you want to consider. So each photoresistor actually has an optimal brightness range. So here in the middle, you can see a graph of the brightness versus the resistance. And you can notice on the two extreme ends, the very dark and very bright ends, that both of them reach a limit. So taking the case of very high brightness, you can see that it's approaching the resistance of the photoresistor itself. So what this entails is you won't be able to tell the difference between something that's bright and super bright, right? So because you can't tell the difference between the two levels, your photoresistor is not going to help you out with measuring the brightness. Same thing goes with the dark end. While the resistance goes from moderately high to very high, okay, over this very narrow range, you can see that we just do not have the resolution to tell the difference between something that's dark and super dark, okay? So that's why you want to try to check out the spec sheets of the photoresistor you want to figure out what's the brightness level range that you want to cover, okay? So on the left, here you can see the various types of photoresistors, right? So as you can see, CDS can pretty much cover most of the visible spectrum, right? So they're pretty safe options. If you want to work with infrared, you have all the various types of lead-based photoresistors, okay? And this is really cool for the next thing, okay? So if you're interested in photoresistors, also check out photodiodes and phototransistors. Those are two different ways to control your circuits using light. So here are some common applications in real life, right? So on the left, we can start off with generic night light. So you can see that photoresistor right in the middle of the image. See that signature wiggly pattern right down the middle. Okay, so this is an old style. And what's really cool about it is that you can see that you can integrate it pretty much anywhere, right? So as long as you have it exposed to light, then you can just fit it. It's really easy, really simple. Okay, so you can also use it in infrared security systems, right? So now you can not only just attach your sensor section, the photoresistor, you can also add a light emission, right? And that'll help you out to determine distance or even connectivity, right? Now, one which you can interact with far more is streetlights, right? So how cities build streetlights is they have photoresistors at the top of their streetlights. And what this does is it tries to check whether it's daytime or nighttime. And if it's close enough to nighttime, they're going to turn on the lights. And when it's close enough to daytime, they'll turn off the lights, right? So this helps you save power in the city because it allows you to use a very low power system to control a very high power system, right? And it's very nice when working around and you have limited power options. Okay, so the next topic will be servo motors, okay? So essentially how it works is you input a PWM signal, and that'll convert it into the servo position based off of the servo's range of motion. So most of the time, most servos have a range of motion between 0 through 180 degrees, where the signal of 0% of a cycle, or the minimum setting possible, will result with 0 degrees, and then 100% cycle will result in 180 degrees. So here you can see the PWM comparisons in the top left. Okay. So a nice thing about servos is actually the wiring is very standardized. So essentially, if there's any major takeaways, you want to remember that the power pin is almost always the red one. The ground pin is always the darkest color available. So that's usually the black or like a very dark brown. And then the data pin is the last one, and it's the weirdest color of them, right? So if it's not red and it's not the darkest color, it's the data pin. So it could be yellow, orange, white, red, you name it, okay? So a key thing to note is that we'll be using the free Arduino servo library, and this will help you out with coding. You don't have to code the PWM yourself. You don't have to code in any of the tracking of the positions, okay? It'll handle it all for you. So this last image here just shows you what's inside of a servo. So how it works is you have classic motor, right? And then you actually have a gear system, which exchanges moving extra distance for accuracy, okay? So this is really nice because if you increase your resolution, you can have very, very high control over your position. And then most servos have a position sensing device for you. So it'll keep track of its position and you won't have to calculate it. It'll all be self-contained. Okay. So when selecting the servo you want to use, here's a few things you want to consider. Number one, do you even want to use a servo? Okay. So the nice thing about servos is they offer the highest control possible over most other motor types, right? They're a little bit on the high price, okay? And they're usually the slowest speed available. So if any of these are an issue, you can also check out DC motors and AC motors. You can choose stepper motors, which is like the halfway point between a servo and a DC motor. And you can choose a parallax servo in case you want a bigger range of motion or a different one, really. All right, then. So now that you've realized that you want servo, here are the main things you want to consider. So is the servo fast enough for your purposes, right? Will it take too long to move around? Will it be too fast, which I doubt it ever will be? Is the servo a reasonable size? Can you fit it in, say, the UGV at an appropriate time? Is the power reasonable, right? So if for some reason that you only have like a 9-volt battery and you need way too much power, the servo won't be good. Likewise, the other direction is if for some reason you require like a nuclear reactor to power your servo and you need to fit it on the UGV, that's probably not a good idea, right? So you want to make sure that you have a good power to fit with your servo, okay? So the last and a little bit on the tricky side thing to choose is the amount of force that you need for your servo, right? So here on the right, you can see an image of the relationship between the speed and the motor torque, like any motor relationship, okay? So here you have your upper limit of what you want to be able to do in the dark blue color, okay? And notice how no, speed and force are inversely related, right? So this relates to how heavy is the stuff you want to move with it, right? So if you want like a really, really nice resolution, right, you want to make sure that you have a 5-to-1 ratio for the amount of force your servo can provide versus the weight of the object you're moving, okay? If you need a little bit of accuracy, but it has a good amount of tolerance, like machining tools or packaging, right, you can get away with 4-to-1 or 7-to-1. And even if you just wanted to move, you can honestly get away with a 1-to-1 ratio of the force. So here are some common places you can find servos, right? So you can actually find them in a lot of vehicles, right? So sailboats, planes, even UAS uses them when building our foamies and even our full-size plane. It's located inside the control surfaces right here. Okay, usually they come with a bunch of either levers or some sort of way to produce a little bit more force so you can get away with a smaller servo and still control the surface. Another common place to see them is in a bunch of automatic machinery. So take, for example, like a CNC machine, right, or a 3D printer. Both of those require very nice precision, so servos sound perfect for their application. And also, you can use servos for pretty much almost any robotics, right? So here you can see it for this RoboDog, and they use it for their legs. So even though you don't need the perfect accuracy, it's still very easy to program with. So that's why they chose servos. Okay, so we've covered essentially what each of the components are, as well as what you should design around them. Now it's time to show you how to even build them in the first place, right? So you have your components, right? You have most of the circuitry parts. How do you stick them all together? So here we'll give you the example problem of using your servo as a dial display to check the brightness of a room, okay? So the goal of this problem will be just show you the schematic, basic code, as well as get you used to servo.h library. All right, so if you find this homework a little bit too easy, come back here, try out the bonus problem of whether or not you can get the LED to show you like a threshold level. So if you want to read at a certain brightness in a room, what brightness is considered the room's too dark. All right, then. So here is the schematic solution to how to make a dial display. Okay. So here are the two components, your servo and your photoresistor. Okay. So the key things to take away is when using the Arduino, you want to be using a PWM pin for your servo. Okay. So this is represented with the tilde sign or the squiggly line next to the pin number. Okay. And then you want to use the analog pin for the photoresistor. Okay. So the analog pin is symbolized with a capital A next to the number of the analog pin. This is also the same way which you would activate it inside of your code. So capital A plus the number of the pin. So for the photoresistor, okay, here's how you'd set it up. In the case of my solution, we decided that we want to place the photoresistor behind the static value resistor. Okay. So this was mostly chosen because I wanted to have a relationship such that as the brightness goes up, then the value to the Arduino would go down. Okay. You can actually switch the order of the resistor versus photoresistor and get the opposite relationship. So as the brightness goes up, the value that the Arduino receives goes up. Okay. So the order in this case would be power, then your resistor, then your analog pin and photoresistor in parallel, and then finally the ground position. Okay. And then now is the servo. So servo, nice and easy. You just need your power wire in this case, you want to attach it to the 5-volt of your Arduino. You want your ground wire or GND. Okay, so if you remember the color scheme, you attach the black wire. And finally, you have your data wire in yellow attached to your PWM pin for the Arduino. Okay, so now that you have a basic understanding of how to attach them to the Arduino, here is an explanation of each of the parts. So why do we need an analog pin? The analog pin helps us out because a digital pin is a polarized value, right? So 0 or 1, high, low, you name it. Whereas in the case of the photoresistor, we want to measure a value between, okay, is it 0 volts, 5 volts, or somewhere in between? Okay. So a key thing to note is for analog inputs, okay, they read from a range of 0 to 1023, whereas when you use the analog output mode, okay, it'll output a value from 0 to 255. Technically, they're scaled the same, however, they have different resolutions, okay? So keep that in mind for the coding section. We chose a PWM pin because we need a low voltage data cycle, okay? So how the PWM pin works is it'll always produce a steady rectangular wave at the duty cycle you need. So if you remember from the last lecture, a duty cycle is essentially just how much you repeat the wave and for how long. So 0 is always off, 255 is always on for your PWM signal. So we chose the 5 volts because most of the time servos have a minimum threshold of 5 volts to operate. Okay, so you can use the 3.3 for the photoresistor if you really want to, especially if your other resistor value is too high. Whoops. Okay. So as I've talked about earlier, the photoresistor position, right? So in this case, I decided to map it from low voltage, high voltage to a high value input to low value input. Okay, you can swap it around, change the relationship. Okay, so if you're not familiar with how to use the Arduino, right, you have a few ground pins. So there's a little bit of a difference, right? So the ground pins closer to the Arduino are actually a little bit better suited to intake current, right? They have a higher limit, but it's marginally higher, right? So it's not too relevant. So just in case that you think that power is going to be a major constraint, just attach to the power section and you should be fine. All right then. So now for the code. All right then. So here on the right, you can see the raw code. It's pre-colored for you. And here on the left, you can see the explanation for each of the commands, okay? So starting at the top, we have the include function, okay? So whenever you add a new library, you always want to make sure to put it at the very top of the page. It just makes it as easy as possible to recognize when you add stuff, as well as it allows you to activate the function at all times within the code, right? Because order matters, okay? So the next line talks about setting up the servo, right? So you want a variable name whenever you want to call your servo. So how you use it is you put in servo space and then the name. So I chose servo1 or my servo, right? It could be anything. Okay, so the next thing would be you want to set up your PWM data pin, okay? So how you do it is here in void setup, okay? You use the name of servo, so servo1.attach, and then you put in the pin number. So if you remember from the schematic, okay, we chose pin number 5, okay? So that's why we put in number 5 right there, okay? And now we've attached the PWM data pin. And then anytime you want to move the servo, what you would do is you would put in the servo name, so servo1.write, And then you put in a value from 0 to 180 to represent your angular position. Okay. So a key thing to note in the code is we added a delay. So you usually want to add a delay when using this library to account for the speed of your servo, because as you know, servos are kind of slow. Okay. So you can go ahead and tune this however you like, okay, based off of how long it'll take for you to get to the end of the loop. Oops. Okay. So the next thing to do is setting up your photoresistor, right? So right at the top, int pin in 0 is we're putting in the number of our pin and we're activating it to analog mode. So you start off with the name of the pin and then the pin number. Okay. So this allows you to just use the variable name whenever you want to use that exact pin. So you set up that pin value. The next thing to do is you want to start measuring that pin value, right? So how you set it up is you put in the variable you want to store it in. So in this case, we chose the integer value, or val, is equal to, and then you use the command analog read, and then you put in the pin number. So because of what we did earlier, right, we can just call it pot pin. Technically, you can also type in the actual pin number itself, so A0. However, it may be a little bit messy. Maybe you might forget which pin is which, okay? So it's usually very nice to add in a variable name for your pin. Okay. So if you remember from the previous slide how analog input and output ranges are actually mapped, you can actually map anything, right? So the cool thing about this function called map, which is innately within the Arduino, is you can use it to rescale from one range to another. So the first bullet point shows you the syntax. So your new variable is equal to your old variable, the lower bound of your old variable, and the upper bound of your old variable, okay? And then you rescale it to the new bounds. So the new lower bound and the new upper bound, okay? So the second bullet point shows you an example of what we would put in. So you can put in the same name technically. So old value is rescaling from 0 to 1023 into the angle 0 to 180 degrees. We put it back in, and now we should be able to write it back in. Okay. So let's take a look at the circuit in action. Okay. So here's the Tinkercad version of the circuit, right? So we have pin number 5. It's attached to the servo. Okay. We have our analog A0 attached to our photoresistor. Okay. And has the extra resistor where the value doesn't matter too much. Here I added a multimeter just so you can check out the voltage values for your reference. Okay. Now, here is the code. It's a little bit messy because I haven't annotated it cleanly, but the code is here, okay? So how you run it is you hit start simulation. And there we go. Okay. So you have your servo. This is an output device, so you can't really control this. But this is an input device, your photoresistor, right? So what you do is you left click and you can drag the value around, right? So notice how the voltage value is changing because I'm dragging it. And if you're too fast, it'll take a little bit of time for your servo to move around, but it'll get there, okay? So if your servo is still moving, you can still send it new commands and it'll go to that one instead. Okay. Yeah. So when it's very dark, notice how the voltage is 5 volts, right? So we're mapping it from low to high, high to low, okay? Okay, so for future reference on where to find the components, right? What you can do is you can import parts. Okay. And then you can also simplify searching, right? So let's see if I can find the photoresistor. Yeah, so here's the photoresistor right there. And we have the servo I chose right here, right next to the DC motor. Okay. Let's back to the presentation. Okay, so Jose, so far so good? Any questions? Questions, no reactions? There we go. Chat response. So far so good. Okay, cool. All right then. So now that I've shown you the now that I've shown you the example problem, right? Here's an activity you can try out on your own, right? So your goal is to make a device that compares the brightness of 2 locations, okay? And then you want your servo to point in the direction of the brighter light, okay? So a little hint that you can start off with is you want to have a threshold to reduce the amount of random noise if you're building this in real life. However, because it's virtual, the threshold can wait a little bit. You can even put like a very small threshold instead. Okay. So if you find this a little bit too easy, you can have a bonus challenge of setting up a state machine from the previous lecture, right? So you can make a state machine and you can have it in 3 modes. So you can have your servo point in the direction of the brighter one or the dimmer one, or even have the servo show the ratio of the 2 brightnesses. Okay. So that's all I have to present to you